Hello everyone, this is Professor Kuehn. Welcome back to my lectures on space, time, and motion from my General Physics 1 course at Wisconsin Lutheran College. Today we'll be talking about Chapter 8 in a Student's Guide to the Great Physics text. This chapter is titled Naturally Accelerated Motion. So you might recall where we've been. We've been looking at Galileo's dialogues concerning two new sciences. The first of those new sciences was the strength of materials, and the second will be projectile motion. We haven't gotten to projectile motion yet. Nonetheless, in the first part of his dialogues, which is the first 2 days of his dialogues, he did talk a little bit about topics that will relate to projectile motion. Specifically, Galileo brought up the topic of falling bodies, and he presented his theory of falling bodies briefly. That was in the context of the 3 men, Salviati, Segredo, and Simplicio, discussing motion through a vacuum and the possibility of a vacuum. You might recall that Galileo he provided his theory of falling bodies in the following way. He said, when you drop an object, that object naturally will attempt to accelerate at a uniform rate. That is, if you drop it, it will gain equal increments of speed in equal increments of time. He'll be more precise about that in this chapter and provide a more mathematical description. Essentially what he's saying is that if you drop an object, its speed will keep getting faster and faster and faster. You might wonder, why then do objects not just keep accelerating and get to infinite speed? Well, he explains. He says, when there's a medium surrounding the object, that tends to check the acceleration, or eventually stop the acceleration. That is what we call drag. So as an object continues to speed up, the drag force increases until finally the drag is so great that the object can no longer speed up. At that point in time, the object will have reached what we call terminal velocity. It'll be traveling at a constant speed. That is the essence of Galileo's theory of dropped bodies or falling bodies. You might recall that there was some pushback against this theory. And one of the reasons why there's pushback is because he's claiming that if you drop an object in a vacuum, then it will continue to accelerate all the time. His opponents said, wait a minute, you're talking about something that never actually happens because there's no such thing as a vacuum. Now, they went back and forth about whether a vacuum is possible, but at the very least you can say no one at this time, and even today, has produced a pure vacuum. So in a sense, Galileo is really presenting a theory about situations that don't actually happen in nature. And this is one of the main criticisms that his opponents had of him. They said, Galileo, you're living in an imaginary world where you're describing a theory in an imaginary world where vacuums exist. We know that in practice you never get a pure vacuum, and so your theory doesn't really apply to our world as we see it. And they've got a point. Every particular situation you look at when you drop an object, there is some drag, there is some medium surrounding it. But I think the strength of Galileo's approach is that while he's looking at particular things and people are dropping particular balls, oak balls or ivory balls or lead balls in air or water or whatever, you're doing particular observations, he is abstracting from particular observations in order to try to arrive at the essence of the thing, to try to understand what would happen under an ideal situation. So he's driving at the essence of falling bodies, and I think that's a good insight that Galileo has. Okay, so like I said, we'll come back to this in a mathematical way in this chapter and the next, but I wanted to remind you where we've been with Galileo's theory of falling bodies. So I have posted on the side of my screen here the section from the text, Chapter 8 on naturally accelerated motion. If we jump ahead to the next page, this is page 106, he says this is the 3rd day of the dialogues. Remember, this is presented as kind of a play or a dialogue between 3 people. This is the 3rd day of the dialogues. The first section is titled Change in Position. And here he gives a summary of what he's going to be talking about in the next few chapters. In particular, he mentions that people were aware in the past that when you drop an object, the speed of the object increases. That's nothing really new. What is new is he finds out a particular way that it increases. And specifically, he mentions that, if I get to the right section, no one has yet pointed out that the distances traversed during equal intervals of time by a body falling from rest stand to one another in the same ratio as the odd numbers beginning with unity. Now, what does that mean? We'll talk in more detail about that shortly, but there's a couple of words in here that you might not be familiar with. So first of all, the word unity. We think of unity meaning together, but unity is also sometimes used in scientific literature as the number 1. So he's saying that if you drop an object and you consider equal intervals of time, let's say the first second of fall, and the second second of fall, and the third second of fall, each of those is an equal increment of time. And he says if you look at the distances traversed during each of those equal increments of time, the first second, the second second, the third second, those distances are to one another as the odd numbers beginning with 1. So if the object falls a distance of 1 during the first second, it will fall a distance of 3 during the second second, and a distance of 5 during the third second, and so on. That's the claim he's making. So he's going to present a mathematical understanding of falling objects, not just a qualitative understanding. Okay? In this first section also, he mentions something else that he's going to be talking about. He says, in the past, people have observed projectiles, cannonballs, artillery, arrows, flying through the air, and they've noticed that they follow a curved path. But he's going to go further. He's going to say this curved path has a specific mathematical form. It's a form of a semi-parabola or a half parabola. And he's going to go ahead and demonstrate that in the coming pages. So here he's just giving an outline of what he is going to be talking about. Okay, let's go on to the next section. This is a section titled Uniform Motion on the bottom of page 106. And here he provides simply a definition. Now remember, when dealing with definitions, you're not claiming the thing actually exists. You're just saying, this is what I mean by this. What is the essence of uniform motion? Whether or not something is actually undergoing uniform motion, whether it exists, is a different issue. But he says you can understand the essence of uniform motion if you understand the definition of it. And here is a definition of it. He says, definition of steady or uniform motion. By that, I mean one in which the distances traversed by the moving particle during any equal intervals of time are themselves equal. Okay? Now, this statement, he chooses his words very carefully. So let me draw a couple of pictures. So if you'll look at my sketchbook here, I'm going to draw a couple of plots to try to illustrate what he means by uniform motion. Okay, so let's suppose we were to plot the distance that an object moves as a function of the time. Okay, and let's suppose for an example, we live here in Milwaukee, Wisconsin. We're on Wisconsin Avenue. I'm at Wisconsin Lutheran College, and down the road is Gillies Frozen Custard. Okay, so let's suppose that I were to get into my car and travel eastward down the road for about a mile to Gillies Frozen Custard. So let's say I start out at time 0, and I start driving. And I drive eastward down Wisconsin Avenue, and I'm traveling at some speed, and I'm moving along. My distance is increasing down the road, and then I get to Glenview Avenue or 84th Street, and there's a red light, so I have to come to a stop. And then I sit there for a little while at the stop sign, and then I decide when it turns green to keep going, so then my distance increases like this, until finally I arrive at this distance of 1 mile down the road, and it takes a certain amount of time. So how much time did it take? Well, let's suppose that it took, 5 minutes to go there. And the distance that I've traveled is, let's say, 1 mile. I don't know the exact distance, but let's just say it's 1 mile. Okay? So that would be a plot of the distance traveled as a function of time during this journey. Okay? Now, let me draw another picture that illustrates the same kind of situation. Once again, I'm going to Gillies down the road. Here's the distance as a function of time. Okay? And let's suppose this time I drive down the road. I drive a little bit slower, but I don't hit any stoplights, and so I'm going at a constant speed the entire time. So once again, I drive at just the right rate, so it takes me 5 minutes to get there, and I travel a distance of 1 mile. Okay, so I get there like this, and I'll make a plot. I'm trying to make this straight here. Not perfect, but there you go. All right, so now one of these is uniform motion, and one of these is non-uniform motion. You can probably see right away that the one on the right is uniform motion. I'm going at the same speed during the entire time. I'm going 1 mile in 5 minutes. So I'm going at the same speed the whole time, whereas in the left plot, I'm going 1 mile in 5 minutes. I'm still traveling the same total distance in the same total time, but I'm not going at uniform speed because I'm speeding up, slowing down, coming to a stop, and then speeding up once again. So how does this relate to Galileo's definition of uniform motion? He says, by steady or uniform motion, I mean one in which the distances traversed by the moving particle, or car in this case, during any equal intervals of time are themselves equal. So the important thing is that he uses the word any equal intervals of time. So let me, to illustrate this, break this into 5 1-minute segments. Okay, so I'm going to try to make these 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So each of these represents 1 minute. So I'll write 1, 2, 3, 4, 5 minutes, and 1, 2, 3, 4, 5 minutes. Okay? And I'm also going to put some markers up here representing distances. Okay? So notice that if you consider equal intervals of time, you're not necessarily traveling the same distance during equal intervals of time in the first case, but you are traveling the same distance during every equal interval of time in the second case. So let's start with the second case. Let's say during the first second, you travel, minute. In 1 minute, you travel a certain distance, right? 1 minute, you travel this distance. Well, what about during the third minute, from here to here, you travel, for the same amount of time, you will travel the exact same distance. So the rise and the run are the same, to use some terminology you might be familiar with. What about during the last minute of time? Well, during 1 minute, you once again travel the exact same distance. So any equal interval of time, so each of these represent an interval of time, they're all equal intervals of time, and these represent intervals of distance, and in each of these, you're traveling the exact same distance. And notice that I could have picked different intervals of time, a half a minute, and seen how far you travel in a half a minute. And in each of those cases, you will still have traveled the same distance during equal intervals of time. That is the essence of uniform motion. In this case, notice that during the first minute, you travel a certain distance, okay? But let's say during this minute right here, well, during that minute, you travel zero distance because you're sitting at the stop sign, right? And then during the last minute, you kind of try to speed up. So during that minute, you travel really far in order to kind of catch up, okay? So you've considered equal intervals of time, but during these equal intervals of time, you are not traveling the same distance. So that would be non-uniform motion. And this would be uniform motion, okay? That's an important distinction to keep in mind, okay? Another way, for those of you who are a little more mathematically sophisticated, you might say the derivative or the slope of the graph of distance versus time is constant on the right-hand plot. That means that the speed is constant, whereas the slope is not constant on the left-hand plot. And once again, I want to emphasize that the total distance in both cases, the total distance in both cases is 1 mile, and the total time in both cases is equal to 5 minutes. So you might say that the average speed in both cases, the average speed is the same in both cases. On average, you're traveling 1 mile in 5 minutes. But the speed at each particular instant is not going to be the same. Only in the right-hand case do you have uniform motion, okay? So tell you what, why don't I stop there? Next time what I'm going to do is draw out some of the implications of this. This is what he talks about on the next page in his axioms. And then we'll talk a bit more about his definition of naturally accelerated motion. So we'll stop here.